So hi everyone. Before starting to the main reconfigurable antenna and transmission line topic, I would like to give a brief introduction regarding Ansys portfolio. We all know Ansys started 50 years ago with Navier-Stokes equation mainly for mechanical engineer. As day passes, it has gained ability to solve the problems related to remaining domains and slowly with the Maxwell equations also. So we have a separate portfolio for electronics also. It is number one in simulation with respect to its other competitors. ANSYS is used by different research centers, R&D parts and companies. More than 95 countries using ANSYS platform for designing this kind of simulation in different domains. Mainly in automatic mainly in automotive industry or in defense R&D as well as in academic also for research purpose. This is one of the important software. These are ANSYS portfolio, which includes embedded software. Then we have safety analysis. Then we have electronics. We have semiconductor, optics and spares. ZMAX, these are the other platform. For Chandrayaan, this SDK from mission engineering, this is one of the tool is used for finding the location, exact location of that particular Chandrayaan. Here we have different companies which includes Samsung, Volvo, then we have BMW, Synopsys, Philips, which using ANSYS platform for their product design. And these are our academic customers, which includes IITs, NITs, triple ITs, and all top institutes who are working with the this portfolio, or you can say this platform for research purpose. These are high frequency tools, which includes HFSS, SI-Wave, IcePack, Q3D extractor, EMC plus, and Charge plus. So in mainly academics, HFSS is mainly dedicatedly used where we can use this tool for antenna designing, metametal wind cell designing, and filters and so on. In case of SI-Wave is mainly dedicatedly used for the PCBs, either it is single layer or multi-layer PCB. We are using it to finding out signal integrity, power integrity analysis. Now we have these important parts, or you can say areas where high frequency tools are morely useful, which includes wireless communication, automotive industry, smart devices, aerospace and defense, biomedical engineering, and so on. So now, apart from that, we have these tools, which includes Maxwell, MotorCAD, Simplora, IcePack. These are mainly dedicatedly used in low frequency tools. And we all know this is the workflow for HFSS, where we are designing the model, applying the meshing, we are giving solvers based upon the application, and then we will run the simulation. If it is giving results at particular resonance frequency, we will stop there. Otherwise, we will again change the parameters and we'll do the same process. So there are two parts, pre-processing part and post-processing part. In pre-processing, all designing and solver application, meshing, everything we are considering. In case of post-processing, what are the results, expected results we are getting, that we can able to see either it is resonance frequency or 3D gain or 2D gain, etc. In case of HFSS, apart from antenna, we can design here wires, connectors, then radar equipments, waveguide, filter, etc. In case of SI-Wave, this is mainly dedicated for the PCBs, where we can able to find out signal integrity calculation, power integrity calculation, EMI, EMC analysis, and so on. In case of Q3D, this is again used for the PCBs, where we can able to find out RLCG component from that PCB. So we all know about the PCB, there are certain tracks, transmission lines. So we can able to see their inductance, capacitance, resistance, conductance value using Q3D extractor. So these are some real-time examples, which include circuit models, cable characterization, transmission line calculation, package lead frames, bus bars, connectors, and our mobile touchscreen. This is one of the important part where all PCBs has to go through this electronic cooling process. The tool name is Ansys IcePack. this tool is mainly dedicatedly used for the thermal management part, where we can able to see how much heat is generating in that particular board. So either it is cheap or IC packages or board level assemblies like Arduino or Raspberry Pi boards, or backplane assemblies, system level simulations, or supercomputer or server room. Suppose we want to check how much heat or temperature is generating in that particular server room or supercomputer room, we can able to see in IcePack. So this is one of the important tool for thermal management part we are using. Next tool is EMC Plus. EMC Plus is mainly dedicated for the cable purpose, where you can see inside cable there are so many small cables are there, then outer shielding is there, and then finally you have one more cable shielding. So these kind of enclosures or cable harness, if you want to find out, EMC Plus is one of the important tool. And the last tool is Ansys Charge Plus. So these are some other examples for Charge Plus: EST gun or arcing in HV system, HV switches, lightning attachment modeling, solid dielectric breakdown. These are the few examples. We already know drone is also one of the important example for this, where the drone is traveling from one place to another place. So in such a case, suppose rain started or thunder started, uh, due to this external change in environment, internal structure of the PCB of a drone should not get damaged. So that is the main thing behind this charge plus tool. Next one is new hot filter. So here name suggesting itself, it is related to filters. We can design it here. Passive filter, active filters, low pass, band stop, these kind of filters. This tool is very easy to use. We have to just give operating frequency and we have to select what kind of filter we are looking for design, and this software will generate that particular uh, filter. In case of HFSS, those are very new software. They can use ACT extension. Here in antenna toolkit, you can able to see more than 22 types of different antenna inbuilt available. You have to give operating frequency and synthesize the design. You will get that particular geometry ready. Directly you can run the simulation. So how you have how the software selected length, width, height, and the each layer values that you can able to analyze using ACT extension. And these are some other examples where these high frequency tools are useful, which includes signal integrity, power integrity. In first figure, here vehicles are traveling from one place to another place. That time we can able to see its gain radiation pattern. Then in third figure, this is related to filters. Then in fourth figure, RF coincide in aeroplane, more than two receivers will be there. Then what will be the scenario? That kind of simulations we can able to see in this fourth figure. And whenever mobile comes in the contact with the human body, due to that device or mobile, human body should not get affected. That's why biocompatibility comes in picture. And the last one is antenna placement on on a particular car. So here also two different geometries are there. One is antenna, other is car model, which are perpendicular to each other, and how this gain radiation pattern will change. That kind of scenario also we can able to see in HFSS. So in 5G, we know in 1G we had only voice communication, in 2G only we had voice and text communication, in 3G we had voice, text, and internet communication, in 4G we had voice, text, internet, and multimedia communication. So 5G is the fastest communication environment, you can say, or technology, you can say, where we can do smart connectivity, smart parking, car-to-car communication, smart wearable, and so on. So this is the whole broad introduction about high frequency tools or HFSS. Now I would like to show you directly the designing part of the transmission line first, and then I'll show you how you can same thing apply in Ansys, where you can able to see this reconfigurable antenna part.
will have separated. Like your now I'm getting.
And now we can able to see the transmission line.
Push excitation, right? This parameter. Parameter is after push excitation, right? Yes, yes. So in the push excitation, so we have two ends. No, I didn't get like when you mentioned two antenna. Because see, in the system, in the circuit, we have two ports. So that means we are simulating two antennas. Okay, like I got it. Like when you like you may have a system where you will have.
Kasturi, you're on mute.
Now, am I audible?
Yeah, you're audible now.
The whole presentation I was on mute.
No. Only during while you were presenting the software.
Okay, thanks. So this is the one of the model where transmission line has been designed. So you can able to see here in the transmission line where these are the solid layers, which includes first of all we'll go with the layer by layer. So this is the ground plane. You can see this is mentioned in pinkish or violet color, and this is the base of this transmission line. Now you check the its position, so you can take photo of the screen. I'll say this for 2 times so that you will note it down, or you can take a photo of the screen. So ground layer we have designed with position -17, 7 -17, 0. We are along the z-axis. X size is 34 mm and y size is 34 mm. So position once again I'm repeating 17 mm minus 17 mm comma minus 17 mm comma 0. We are along the z-axis and x size is 34 and y size is 34. Then next layer comes, that is FR4 substrate. This is the substrate you can able to see on the screen. So here the positions are again -17 comma -17 comma 0. X size is 34 mm, Y size is 34, and height of the substrate, which is mentioned in Z axis, which is again H, and that is 1.6 mm. So once again, I'll repeat the positions: -17 comma -17 comma 0. X size is 34, Y size 34, and Z size is 1.6 mm. Okay. So now the third layer will be the transmission line. So this is the transmission line dimensions where positions are -17 comma -1 comma 1.6, and x size is -32 and y size is 2. And apart from that, on exactly on the center of transmission line here, you can able to see we have some strip lines. So in that designing of the strip lines, we have to again create a slot on that. So for that, dimensions you can able to see on the screen. Take a photo of this. Positions are -1 comma -1 comma 1.6. We are along the z-axis. X size is 2 and y size is 2. Then close this and then subtract this transmission line through this slot. Then you will get this one blank part. So now after that we have to create here 4 slots where we are going to assign, this is C1, C2, inductance L, and resistor R. So now we will see one by one. This is the C1, this is C2,
Okay, Sukesh, yeah. Thanks, Naveen.
L1,
With that query, as of now, we don't see any option to
and
see the
R.
licensing what Sukesh is asking.
So,
Let me have a word internally. Probably I can.
so
Okay, then.
this is the C1.
I think it's recording. Sorry? No, I don't. I will share you this recording over email for your reference. Like you can have it. Yeah, please. I think you must be fine with those voltage and power values and all.
So here positions are 1, comma, minus 1, comma, 1.6. Axis along the Z and X size is minus 0.5 mm and Y size is 2. So similarly, this is for C1 and this is a C2, exactly opposite to that. So now here you can able to see again the dimensions for C2, where you can able to see the positions minus 1, comma, minus 1, comma, 1.6. We are along the again Z axis. X size is 0.5 and Y size is 2. Now go to L. L is the middle part where this is the inductance where positions are 0.5, comma, minus 1, comma, 1.6. We are along the Z axis. X size is minus 0.5 and Y size is 2. Now this is the dimensions for R. You can take a screenshot of this or you will get a recording of this session where the positions are minus 0.5, comma, minus 1, comma, 1.6. We are along the X axis. X size is 0.5 and Y size is 2. So once it is done, we have to give a boundary conditions to each this lot. So for that C1, we have to just right click on that particular slot and then go to lumped RLC boundary and here type C1, select first series and C1 is capacitance. So only select capacitance part and where 32 picofarad value we need to give. Click on OK. Similarly for C2, this is for C1. C2 we have to do the same thing. Again go to RLC boundary and then give name C2. Capacitance is 32 picofarad. Now the third point is inductance where L1 it is showing here where L1 is inductance and in the RLC value click on inductance and you can able to see its value 0.4 nano Henry. Okay, and next one is R1. So R1 is resistors. It is in series value where resistance is 10 kilo ohm. We have kept. You can keep any value. You have to check either the diode is on in condition or off condition. When it is on, resistance across the diode will be the minimum, like in ohms. And suppose it is open, diode is off condition and switch is open. In that case, the resistance value will be more. So keep in kilo ohms. So likewise, we have to change the values in this RLC boundaries. Okay, once it is done, again give the radiation boundary condition and right click on that and create uh, open region and here select 2.4 operating frequency, click on radiation and click on OK, you will get this radiation box. Okay, so inside that we have transmission line. And then we'll run the simulation, go to addition check and analyze all. Simulation has been started now. Now go to result and see the S parameter plot. This is when diode is off. Now I'm going to change the boundary conditions. That RLC boundary conditions I'll keep. Now the diode is on condition so that we can able to see the result. Diode is off now, so you can't get any resonance at 2.4 gigahertz operating frequency. We'll see when diode is in on condition. Now we'll see the results. So you can see it here when diode is on condition is in on condition. This is the resonance we are getting. Right click on that, click on marker, add marker. This is at 2.2, this is at 2.3, this is at uh, 4 gigahertz. So likewise, we can change it and we can reconfigure through the uh, transmission line. Now the next I wanted to show about the antenna. This is about the transmission line. Same concept we are going to use for the reconfigurable antenna also. So this is the antenna. When all diodes are on, we will see, and then when all diodes are off, we will see. So this is basically CPW antenna. You can see here on the screen. This is the ground plane. You can see this is the patch, and this is the substrate. Okay. Now you can see here in the patch, this is a transmission line. Okay, and here the patch is available. I want to connect these all parts which are available on the upper part of this antenna. Here I have connected three different diodes. This is diode 1, diode 2, and diode 3. You can able to see over here also in the boundary conditions. This is so here this is diode 1. This is half part of that. This is second half. You can see here boundary conditions are getting changed. Diode 1. Then this is diode 2 here. This is diode 1, diode 2. This is diode 2. Now we'll see diode 3. So at this point, you can able to see this is diode 3. So we have given all the conditions for that. The same thing, like right click on particular slot and then uh, go to assign boundaries and select lumped RLC, and here we have to select a particular value for that. So what are those values? You can able to see here. For when it is parallel, then resistance value, like diode is in on condition, then minimum resistance will be there across it. So that for that I have kept 4.7. If it is off diode, if it is diode off, then here you change the ohm into kilo ohm, so that maximum resistance will available in that particular point. Same thing you have to do for remaining diodes also. One is inductance and other is resistance. I didn't use here capacitance. There are two ways basically for creating this kind of geometry. In the first example, in the transmission line, I have shown you in front of you. C1, C2 separately I have created, and in between R and L I have kept. In this case, I'm not using C1, C2. I'm only using L and R, but inside this I'm going to select, suppose capacitance is available, then I'll click on here capacitance and I will add the capacitance value. So it's up to you which method you are going to use, but this is if you want minimal slots, then go for this, where two slots only you need to design. One will be resistance, other will be inductance, and you can add there then on off based upon this. And if you need to add capacitance, then you have to select or that those value in click that particular capacitance value and add the details. So likewise I have done for the three diodes. So once again click on the validation check and run the simulation. So here we can see once these all three diodes are in on condition, in that case we can able to see the resonance. You see here. This is the S parameter. Yes. So this red line indicates when all three diodes are on. And here I have added this blue line. You can able to see this is for when all diodes are off condition. I have extracted it by I have saved the results previously for you can able to see when two diodes are off in that, or all three diodes are off. So I will just click on that and I'll open that particular results. It will again create the graph. So this is for all diodes. Blue line indicates all diodes are in off condition. This red line shows all three diodes are in on condition. So in this case, we will have total 8 possible conditions where these three diodes either on, one is off, or three are on, or two on, one off, or two off, one on, likewise. So 8 possible conditions we can able to achieve here through these diodes. Since we already know that there is a concept, like I'll write it here in paint. So when we have this, we already studied this in digital design. Suppose three diodes are there or two diodes are there, then first I'll start with one. When one diode is there, there are only one possible condition, 2 raised to 0, that is one possible condition. And then when two diodes are there, 2 raised to 2 possible conditions are there, means four total conditions are there. And when three diodes are available in the circuit, then 2 raised to 3, 8 possible conditions are there, and so on. Like 4 diodes are available in the circuit, then 16 possible conditions are there. So likewise, we have to check, and in this design, we have a 3 diodes, means 2 raised to 3, 8 possible conditions are available for the design. So that's how we have to check the results. Apart from that, I would like to show you the gain for this particular result. So again, right click on result and go to far fields, and here click on radiation pattern, gain total, and dB you have to select, and just click on new report. So it will show you the results. You can able to see these are the 8 possible conditions, and the graph has been also plotted for 8 possible conditions. Now I would like to show about the radiation pattern in 3D. So we'll see that part also. Over the sweep we'll see, and this is the result. So total gain is 0.96, and it is like a apple, you can say. If I'm cutting it horizontally, uh, and it is exactly like apple. If I'm cutting it horizontally and I'm seeing it from one side, it is approximately looking in H shape. And if I'm cutting horizontally and seeing on the top, then it will look like a circle. So it has omnidirectional radiation pattern if you're seeing on the top view, or along the from the x-axis, or if you're cutting it vertically and seeing from the any sides, it will show in a H shape. So these are the two possible ways to check the radiation pattern